Hello and welcome back, everybody. Today we're going to talk about a few topics that are often found in relation to each other. That's going to be electronic control braking, regenerative braking, and hybrid assist systems. Electronic control braking relies on the fundamental principles of anti-lock braking system hydraulic operation. Through the three-stage process of isolate or hold, decrease, and reapply pressure to the brakes, is all going to be accomplished through electronic means of valving and pump moving fluid through the system, and often is dependent on the driver's input to the braking system. Many newer vehicles are coming out standard with adaptive cruise control or LiDAR systems that can sense an object approaching from the front of the vehicle or the vehicle approaching an object and will self-apply the brakes automatically before the driver has the time to react to the brakes and apply the brakes manually from the driver's input. These systems will often be controlled through an integrated assist system that contains everything that contributes to the braking system hydraulic function. So this has a reservoir, this has an accumulator, it has a pump assembly, it has solenoid valve assembly. The control module may be serviced with the unit, may be serviced separately from the unit. This is going to give all the function of the hydraulic system the features for electronic control braking. The control module is going to receive various inputs from the system, most of which are going to be from components housed within this assembly. Aside from the pump motor itself, there will be pressure sensors and there will be linear solenoids. Linear solenoids can be conceptualized more easily through a ball valve. So this is a mechanical valve. When the handle is positioned 90 degrees to the line passing through it, it is closed. So right now, there's zero flow through the valve. With the handle parallel to the line, it is in the open position. With the valve open, we have flow. With the valve closed, there is no flow. Now, linear solenoids can be either normally open or normally closed, depending on where they are in the system. A normally closed solenoid valve will be closed when there is no power given to it. Others can be normally open and will default to the open position when there is no power to it. This can be a little confusing at first when we're talking about whether something is mechanically open and closed versus electronically open or closed. So an electric circuit that is open means that we do not have a continuous loop of current flow through the circuit, meaning the circuit is de-energized. Mechanically open does not always correlate to electronically open. So pay attention to the details when there is information regarding valves in the default or normally open or closed position versus the circuit, which may be electronically open or closed, or energized or de-energized. By configuring multiple linear solenoids throughout the hydraulic circuit of the system, by opening and closing different valves in different sequences, we can route fluid pressure to different areas of the brakes, and the system can react to the desired versus actual conditions. In the PowerPoint slides or the PDF slides, you'll see a couple different variations of Toyota Prius electronic brake control hydraulic circuits. And this will have several different valves in the system. It looks a little confusing at first, there's a lot going on, but keep in mind, it's breaking down what's occurring inside of one of these units. Some of the inputs that we will be discussing are going to involve the stroke sensor, which can also be considered the brake pedal position sensor, or what the driver's input or desired brake position of the brake pedal is going to be. The pressure sensors that can be in various places throughout the hydraulic circuit, and there will be multiple pressure sensors to report information back to the control module as to what the actual pressures are for each part of the hydraulic circuit. There will be the pump state, whether the pump is energized or de-energized, on or off. The pump command, which is the desired command of the pump, whether the system should be commanding the pump on or off. And those two are going to correlate together. If the pump is commanded to energize, the pump state will indicate whether or not the pump is in fact turned on or off. Pump state and pump command are both inputs to the control module, indicating what the desired and actual state of the pump are. They should match, and if they don't, there will likely be a fault code associated with it. Same with linear solenoid state and linear solenoid command. There may be other inputs depending on the vehicle and the application. That should all be looked up in the service information. For the basic operation of what we're going to discuss today, we'll focus on these for now. Outputs are what the commands are going to be from the control module. The control module is going to receive the inputs, and based off of the inputs, determine what outputs to command. Whether that's going to be energize the pump, energize one or more of the linear solenoids, or any other of the outputs that may be integrated into the system. The main types of linear solenoids in electronic control braking are going to be the master cylinder cut solenoids, linear apply solenoids, abbreviated SLA, and linear reduction solenoids, abbreviated SLR. The apply solenoids and the reduction solenoids will often be associated with which position or which wheel that hydraulic circuit applies to. So a right rear linear apply solenoid will be abbreviated as SLA-RR, and the same for the reduction solenoid would be SLR-RR. And as I mentioned before, linear solenoids will either be normally opened, abbreviated NO, or normally closed, abbreviated NC. This can be due to a safety feature built into the system in case of power loss. Without any electronic power, or in the event of electronic power failure, the system still needs to be able to be operated manually from the driver's input at the pedal in order for the system to apply the brakes from the driver's command manually through the hydraulic system. During normal operation of this system, the driver's input to the brake pedal is an input for the pedal position in the system. The control module is going to determine what position that is and adjust pressure to the system and to the corresponding valving in order to slow the vehicle down effectively. The driver is applying hydraulic pressure against the master cylinder cut solenoids, which are going to isolate the driver from inputting any hydraulic pressure into the system. And that hydraulic pressure from the driver inputting force on the pedal is going to go into what's called the stroke simulator. The stroke simulator is a hydraulic component built into the integrated assembly that simulates the feeling of applying the brakes. It has a couple stages of springs inside to mimic the initial, the primary, and the secondary stage of a typical master cylinder, so the driver doesn't feel anything different. If it had no resistance, the driver would be able to apply the brakes probably more than desired without becoming accustomed to the system. By having a stroke simulator, a person can go from driving a conventional brake hydraulic system vehicle to an electronic control braking system vehicle and not have a learning process as to how to drive the vehicle and how lightly to press on the brake pedal. So it's all calibrated to be pretty even with normal brake feel on a typical master cylinder hydraulic system vehicle. In the event of electronic failure, most of the time, the master cylinder cut solenoids will be energized once the vehicle is turned on to the closed position. Master cylinder cut solenoids, which are linear solenoids, will be mechanically closed when energized, when the system is active. On some systems, in the event of an electronic failure, the master cylinder cut solenoids will default to the open position, effectively allowing hydraulic flow from the driver's input at the brake pedal to the hydraulic circuit of the system to apply the brakes. Now, it may only apply the front brakes, it may apply both front and rear brakes, depending on the other valves of the system and their normal state, or their default state. With the cut solenoids in the closed position, so the system is powered, but the valves are shut, isolating the driver from the hydraulic system. As the driver depresses the brake pedal, pressure will build in the master cylinder portion of the hydraulic system. The pressure sensors upstream from the cut solenoids will report their pressure values as inputs to the control module. As the control module interprets the amount of pressure coming in, it can determine how much pressure it needs to generate at the pump and control the linear apply and the linear reduction solenoids to apply and reduce pressure to the brakes. On Toyotas, the pressure sensors, 0 psi pressure sensor voltage value to the control module is going to read 0.45 volts, plus or minus a few hundredths of a volt. And then from there, it is about 650 psi per each 1 volt increment. So calculating out a conversion factor may be necessary when determining whether or not a pressure sensor is reporting an accurate voltage value. The example I've drawn up here is 1.45 volts is equal to 650 psi, with 0 psi being equal to 0.45 volts and 650 psi per volt. 1.45 volts equals 650 psi. Another example on the same system, how much pressure is equal to 3.45 volts? We can drop the 0.45 or subtract 0.45 from the voltage reading to get our 0 point, and then calculate 650 times the remainder once the null value is subtracted from the voltage reading. At 650 psi per volt times 3 volts equals 1950 psi, and that is equal to our voltage reading of 3.45 volts. Since the electronic control braking systems can generate pressure on their own through the control side of the control unit and the use of the pump and the accumulator storage pressure, these systems need to be de-energized and purged of all pressure before they are open for service. This means that following proper safety precautions and procedures before working on the system must be followed before opening any part of the system. Newer vehicles use key fobs without the use of an actual key to insert into the vehicle's ignition. These systems transmit frequencies between the key fob and the control unit and the immobilizer and can possibly energize the system as the driver is walking up to them. Oftentimes, these systems will perform their self-test safety check as the driver is approaching, so when they start the vehicle, the system has gone through its safety check and can tell the driver whether or not there are any problems detected. During this time, that pump may energize the system and pressurize it. So if you're working on one of these systems, make sure the key fob is nowhere near the vehicle and is at a safe distance away. If you're working in a shop, that might mean putting the key in the office far away from the vehicle. Other systems may energize the system and perform their self-test hours after the vehicle has been shut off and has gone to sleep. Depending on the manufacturer and the vehicle will depend on what type of self-test procedure the vehicle will do while the vehicle is not in use. Always refer to service information before working on a system or opening a hydraulic system. One other thing I will mention about these systems is that they're often part of an integrated unit. Most assemblies will not be serviceable down to their individual components. They will likely be serviced as an assembly, and that may or may not include the control unit portion of it. When testing for a fault in these systems based off of a code or a symptom, it doesn't always mean that you need to find out exactly where the fault is within an integrated component. Only that it is either within the integrated component itself or in a control module itself. If this part is only available as an assembly, condemning the assembly is all you need to do. Once you arrive at that conclusion, there's no further testing needed and the replacement or repair can be performed. When replacing a unit, there will often be a procedure involved with installing a new unit and configuring it to the vehicle. Sometimes that may involve using factory programmed software to match it to the VIN of the vehicle. In addition to the hydraulic component of electronically controlled braking, there can also be integration with hybrid and electric vehicle high voltage systems that can regenerate power by using some of that vehicle's kinetic energy and converting it back into potential energy in a battery source. Just like an electric motor draws amperage to run and operate, it will also cause drag on a system if it is energized to generate power. Think about a generator or an alternator that is being turned by the engine. As the alternator is converting that mechanical motion into electronic power to power the system on the vehicle, that is taking power from the engine in order to do that. It's not free energy. As the power unit increases its charging ability based off of the vehicle's kinetic energy, it's going to slow the vehicle down. And it can do so very efficiently to where the system doesn't energize the normal braking system of the vehicle until you're below certain speeds. Usually that's under 10 miles an hour. Could be under 5, could be under 7, depending on the vehicle. It may not energize the actual braking system until it's brought down to those speeds, which means that most braking is done by regenerative braking or charging the high voltage battery. In order for a vehicle to be equipped with a system capable of regenerative braking, the requirements will be that it has electronically controlled braking to start with, electrical storage or a high voltage battery, one or more motor generators that can propel or generate power, and computing power. Computing power mostly is necessary due to the management of high voltage systems, as energy is more efficient or less efficiently produced by the generator, and for safety operation of the vehicle for the driver and occupants, and for the management of that power. Most of this will be reflected through the data that we can observe on a vehicle. Again, we'll be using the 2016 Chevy Spark and interpret some of the values that are accessible through the Modus scan tool. We may have to access different modules in order to get the information that we're looking for. And not all information may be in one location. There also may be some PIDs that are shared between different modules or different menus. And this is where the CAN network comes in, where the modules share information with each other, and that communication helps with each of the modules' functions, so circuits don't have to be redundant. Okay, I just pulled into a parking lot. And I'm going to perform a few low-speed braking maneuvers just to collect some data. I'm going to go back to the back of the lot here. So I'm going to go about 15 miles an hour and then slow down to about 5. There's 15, 17, and braking down to... Okay, I felt the regen stop working at about 4 miles an hour. I could feel a little bit of a nudge in the vehicle when it got down to 4 on the speedometer. Also on the speedometer is an indicator that shows when power is being consumed and when power is being regenerated. So this actually regens down to about 4 miles an hour. And at that point, it may be electronically controlled braking on this vehicle, or it may be hydraulic. It could be either or both. Now, as you can see, I'm in a parking lot, and I'm going to accelerate and then apply the brakes. And what you'll see is power consumption here, and then regen down here, and it will change depending on how hard I accelerate and how much regen there is, or how much I step on the brakes. And then I'll show you at 4 miles an hour how it turns off the regen. You'll see the regen icon go black. So here we go, accelerate, consuming power, coasting, regen, braking, regen, slowing down to just under 5 miles an hour. So 5 miles an hour, 4 miles an hour is when regen turns off and electronic braking control takes over. So right now, we're reading in the hybrid EV data. So we're reading mostly what the battery is doing. And included in there, it shows regenerative braking and a couple other items on the data list. Notice that there are redundant sources or data points for regenerative braking. Oftentimes with systems that are safety related, you may have redundant information, meaning that you can have a fault in one of the circuits and maintain integrity in a different circuit, and the redundancy keeps the system working accurately while still alerting the driver of a fault in the system that can be addressed by a service technician. Unfortunately, on this list, we cannot compare regenerative braking with the vehicle speed. We may have to go into another menu. So I'll poke around a little bit, see if I can find something that we can compare a little bit better, and look at some other data. Farther up on that same menu shows our hybrid EV battery. This is in the state of charge in percentage, SOC. Started out at 94%, now we're at 89%. And then the hybrid EV battery pack current in the amperage, and it shows that fluctuation there. So I'm sitting here in the parking lot, vehicle is not moving, and I'm monitoring the brake pedal position. So I'm barely holding it just enough to keep the vehicle from moving. If I release it, vehicle starts to move a little bit, and to stop the vehicle is all I need right there. Now I can continue putting more pressure on the brake pedal, and the position is going to change. And you can see the reaction occurring with the high pressure accumulator at the top, decreasing pressure, and it's at 3,868.4 psi right now. And if I release, the pedal and then reapply, I can do this and deplete. And there I just felt the pressure increase and the motor engage. So as I depleted pressure from it, I could feel the pump starting to pump pressure, and I felt that against the brake pedal. So the pump in the electronic controller is building pressure to keep a high pressure accumulation. Brake pedal position is going to change in relation to how much pressure I apply to it. So the lighter the application, the less pedal movement I have, and then the more I step on it, the more it increases. The brake pedal position is active versus inactive. That's why we just see a square wave on or off signal. So as we deplete that pressure again, there it's pumping back up. You can see the value increasing right here. So I'll deplete it, then it pumps back up. The pump motor enables and disables in order to restore accumulator pressure. On brake pedal position, this is another one of those redundant circuits. It's actually an inverse signal with a high signal and a low signal. So right now we're monitoring the low signal, and then right below that is a high signal. You can see that each graph perfectly mirrors what the other one is doing. That redundancy in those opposing circuits is a safety feature in the system. They're keeping each other in check by monitoring them both directions. It creates a redundancy and a safety feature in the brake pedal position sensor circuit. So right now I'm going to drive up a hill, and the speed limit on this road is 30 miles an hour, so we won't have a lot of momentum. So it should be drawing a fair amount of power to go up this hill. It's fairly steep. And then when we go down the opposite side of the hill, it's also, I believe, a 30 mile an hour speed limit. And we'll see what the power consumption versus regen is. And right now our range is 52 miles. So we can see that reflected in the range oftentimes. And depending on where you're driving, you may increase your range during your trip and then decrease your range going the opposite direction. There's no such thing as free energy, so it's always going to decrease in the end. Going up the last little part of the hill here, trying to stay right on the money at 30 miles an hour. Even when I'm coasting, there's a little bit of regen occurring, just a little bit. And if I feather the accelerator, I can't really balance, right there, maybe a little bit. I can almost balance it to where it isn't under regen or power consumption at a neutral state, but it's either going to regen or it's going to consume power. So we'll be going down the hill here in a moment. Okay, as we go down the hill, 30 mile an hour speed limit, and it's under regen right now. So the range reduced to 51 miles of range, and it's at 52. Now we're at 53. So what I get from that is that I went downhill longer than I went uphill. So some of the information that's available to the driver here is our range, which is our battery state of charge and the miles next to it. Doesn't give a percentage reading on the state of charge, but we were looking at that on the data, and it gives you a mileage range. Gives us our speed, our direction, and whether or not we're consuming power or under regen. So as we consume power and regen until regen disables under 5 miles an hour, and then we're under electronic control braking. Due to the restrictions that we're facing at this time, there's more that can be done if we were in a class setting, much like every other topic that we've covered up to this point. But I hope that some of this information was helpful to observe through the means of these video recorded lectures, and the rest will have to be done in person when we're back at school at the college, in order to get your hands actually on some electronic vehicles, hybrid vehicles, and service on the systems, so you can test drive and record data and monitor some of these systems on your own. So this is the final video in the series for this class. And we just covered electronic control braking, regen braking, and hybrid and electronic vehicle assist systems. It's been a lot of fun. Thank you.